that is chapter 1B and C, I think, in the Atkins book. So right now we're at the very beginning of the Atkins book. Maybe what we're doing here is review anyway, but it's an important thing to realize what is going on. It's really important because what we feel, what thermodynamics deals with, what you've been trained to think about is temperature and pressure as something like it feels hot, it feels cold, or there is force applied to it. And what we realized is that we really much more have to think of in terms of velocity and momentum and kinetic energy of particles. So that is a change of thinking we have to do, and it's important. There's things for ideal gas. I think you learned them way back when already, so we don't need to go over them. Okay. But what we came out of it, we did some very fundamental math over here, and then at the end of that math, we found, oh yeah, the temperature is just a measure for the kinetic energy of the particles, nothing else really. Whether we say temperature or whether we say that the kinetic energy of the particles on average has a certain value is just the same thing. So when we say it's hot outside, we're really saying, aren't the molecules fast today of the air? That is something we need to keep in memory all the time, because that is really the essence of chemistry. Okay, then we found that there was in the x direction 1/2 k Boltzmann times T for the average kinetic energy. How much would it be in the y direction? Probably the same. There's no special direction. And in the z direction as well. So if the particles on average have 1/2 k Boltzmann times T in the x direction, they will have the same here and the same there, and we'll end up with 3/2 k Boltzmann times T for their average kinetic energy. And those averages, of course, just add up straight away. Let me just put a blank slide up here so that I can write that. Now, that tells us about the average. But what we really have to learn about is not the average, but we have to learn about the distribution. Meaning that not all particles will have the same kinetic energy. Not all air particles will. Some of them will be pretty slow in the x direction, move fast in the y direction, or fast in the z direction. And others will be just fast because they move fast, and others are slow, and next time they bounce against each other, they switch places, and the other ones will be fast, and the first ones will be slow. So there are always fast ones and slow ones. And so we need to figure out what fraction is actually fast and what fraction is slow. Because if we think about chemistry, we think about chemical reactions, and if we think about chemical reactions, they will probably happen when gas particles hit each other. And only the fast ones will have enough energy to hit when they hit each other to sever the old bonds and form new bonds, and the reaction will happen. And so it's important to understand what fraction of the particles are actually fast and what fraction are slow. And so we need to understand how the probabilities are going on. And so we need to understand distribution functions. Distribution functions give us information about what fraction of the particles are in which interval of the property we are interested in. Yeah, that's very good. So distribution functions are something mathematical. If I have the distribution function, then the integral over that distribution function of all the range that the value could be needs to be 1. If the distribution function gives me something like a probability for a property to be an interval, then if I have as an interval all possible values of that property, then I probably need to have 1 when I integrate it. In some property, it will be. So the integral of a distribution function integrated over its whole range of definition, and the whole range of definition depends on what property we're looking at. For the velocity in x direction, it is minus infinity to plus infinity. For the speed, which goes from 0 to infinity, it is from 0 to infinity. There's no negative speed values. Speed is always how fast it is in whichever direction it goes. So depending on what the property is, the interval at which the distribution function is defined is different. But if I integrate it over the whole thing, then I need to get 1, it's normalized. And then, if I have the distribution function, then I can find averages with this. If I have the distribution function g, which is maybe the distribution function for the velocity in x direction, if I make an integral of the whole range of the velocity in x direction, which is minus infinity to plus infinity, I can be infinitely fast in this direction and infinitely fast in that direction, and integrate over Vx, and put the velocity in x direction in front over here, then the result will be the average of the velocity in x direction. With the average, these larger, smaller kind of signs. Okay, that is how I can use the distribution function. It will give me the average. Now, if I want to know what's the average of the velocity squared, I'll just do this one. So whatever function of the velocity in x direction I'm interested in, I just put it in here. I just put it in here, and I will get the average of that. I can also be interested in asking myself, what fraction of the particles are in velocity interval from velocity 1 to velocity 2? And then I can do it like this. I integrate from velocity 1 to velocity 2 over my distribution function, and it tells me which fraction of the particles are within this velocity interval. If that were from minus infinity to plus infinity, it would be 1, all of them would be. But if I have a shorter interval, if I'm just taking a subset out of this, then it will give me the fraction of the particles. And as such, the probability that a particle is in that interval. To get a real probability out of the distribution function, I need to integrate it over the interval for which I want to find the probability. The function g itself, my distribution function g itself, is somehow a measure for the probability of a particle to be at a certain velocity, but it is not a probability. Distribution functions can be larger than 1, and you know probabilities are never larger than 1. Distribution functions can be larger than 1 for very small intervals, so that if the this interval is really small and this is larger than 1, the integral is still smaller than 1. And so only these integrals are really representative of probability. So it has to do with it where I have the highest values for my distribution function. I also have the highest probability for my particles to be there. But mathematically, in order to get the probability, I really always need to integrate over an interval for which I want to have the probability. So say, if I have an oxygen molecule in the air impinged with at least 10,000 miles per hour onto your paper in front of you, then that oxygen particle had enough kinetic energy to oxidize your paper and convert the cellulose at least partially in CO2 over there, make damage to your paper. Do the first step of burning the paper. Then I can ask myself, what fraction of the particles in this room, of the oxygen molecules in this room, will have at least that 10,000 miles per hour of speed, or velocity in y direction, whatever I have here. And then I can calculate that by looking for the velocity in y direction from 10,000 miles per hour to infinity, do that integral, figure out how many of those particles have that velocity. By multiplying this probability I'm getting with the total number of particles, and I know how many total particles in this room will have. Does it make sense? It's how you work with distribution functions. So, distribution functions are helpful. They can tell us something about, will the reaction go? Will the particles in the oxygen molecules in the air have enough energy in order to burn the paper in front of you or not? So it would be nice to know what is the distribution function for the velocity in x direction in this room for gas particles, or really anywhere. And it turns out that there is one distribution function in nature, which is the one if we don't know anything else about the system. The one kind of for dummies, for systems where we don't have information. And that distribution function can be derived by making some magic in math, really, without knowing anything about our system. And I'm going to do this magic in math to you quickly over here to show you that there is really no information I'm providing about this is chemistry and this is gas and this. And I still get out the distribution function. It's that universal. So for that, if I want to have a different distribution function g over here, I assume I just know. I assume I know already my g of the velocity in x direction. And in the end, I do know it. Now, if I have a g of the velocity in x direction, then that will be the same thing as the g for the velocity in y direction. There's no special direction in nature. And that would be also the same for the g in the z direction. So I can multiply them all with each other. And then, when I'm multiplying them, I will get a new distribution function, which I call d over here. And this new distribution function will tell me what is the probability that a particle has velocity in x direction, velocity in y direction, velocity in z direction, right? But now again, there is no special direction in space. All directions in space are the same. And so, this distribution function over here is really a function of the speed of the particles. It's not a function of the velocity of x direction, y direction, z direction directly, or it is as well, but it's really the probability, something about the speed. No matter whether the speed is pointing in that direction, or this direction, or any other direction, the probability has to be the same. Neglected gravity. And so, this is here the property of the speed, where we all know that the speed v is the root of vx squared plus vy squared plus vz squared. Okay. Everybody buying that? Anybody having a problem with this one? Now, if I have this one, I can do the first derivative of this function by the velocity in x direction. Okay, d of v by d, velocity in x direction. Now this one here this one depends on v, and that depends as a derivative by velocity in x direction. So I'd rather not do this directly because it doesn't work so well. So what I'm going to do is d by dv by dv and then dv by dvx. That's just math, correct? I can do that. And the v, how v depends, the speed depends on the velocity in x direction. I have it here. And so then this one here is dg of the x by dvx. But this one here doesn't depend on vx. That's just a number. So it's just multiplied by g of vy and g of vz. They don't depend on vx or vz, so that they are just numbers in this context. They just multiply them on. So, what is this one here? This one here, I can just say that is the first derivative of dv, correct? d3. That is this. The next thing over here, dv by dvx. Now let's do the first derivative. The outermost first derivative gives me 1/2, so this one here is 1/2 1 over the root, with the root being whatever is over there, right? That's the outermost derivative. I take the first derivative of the root, I get 1 over the root. Now, the next thing is I take the first derivative of this one and multiply. That is 2vx. And then these ones don't depend on vx and vy, so they are 0 in my derivative. So this one here is the first derivative. So this one over here is this one. Does it make sense? Everybody fine with it? Okay. And I'm just saving writing, so that's I'm writing the root over here, but it's the root of that. Okay. And that is, of course, dg of dx by dvx, g of vy, g of vz. Now, I could do the same thing with the first derivative by vy, correct? I could do the same thing now saying, okay, now I want to do my derivative in the y direction. If I were to do that, let's guess what the result out of this one is. Let's see what the result is. That is d prime of v, and then it is still 1/2 and 1 over the root and 2vy now. That's the only difference if I had done the whole thing by y on the left-hand side. And on the right-hand side, it will be now dg of vy by dvy, and then g of vx and g of vz. Correct? Otherwise, it's all the same. Anybody having a problem so far? Okay, if this is fine, then you'll probably all allow me now to divide by each other. I have this truth, I have that truth. Unless they are always 0 or something bad happens, I can divide them by each other. So I divide them, right? I divide them on the left, I divide them on the right. Now if I divide them, then this will go away because it's the same. This will cancel. This will cancel. This will cancel. But the vx and the vy will stay. The vz will also cancel. So I'm getting actually a really manageable small formula over here. And again, the only chemistry which I do over here is that I know that in the Vx and the y direction, everything is the same. Otherwise, I don't have really much of it. So, Vx over Vy equals dg of Vx by dVx times g of Vy, the whole thing here divided by dg of Vy by dVy times g of Vx. Okay, if I have this one here, if I have this equation, then the next thing I can do is separate everything which has to do with Vx on one side and everything which has to do with Vy on the other side. So, here I have Vx, left side is my Vx side, then I need to divide this one here over, divided by g of dg of Vy, Vx by dVx, and then I also have this one over here, which gets over here, g of Vx. And then on the right hand side, I can do mass, or I can say it needs to be the same thing. So it is Vy, g of Vy divided by d of g of Vy by d of Vy. Okay. I was able to separate them completely. I have only things which depend on Vx on the left hand side. I have only stuff which depends on Vy on the right hand side. That's not always the case that I can separate them that way. But here I can. Which means I can now change Vx without changing Vy. I can do that, they're independent, correct? But this equation always needs to hold. And so that equation will always hold over here. I can say that that equation over here needs to be a constant. Because if it were not a constant, if this were not a constant, which I might call alpha over here, if this were not a constant, then I would change Vx, and I would have a problem because all this term doesn't depend on Vx and cannot change. Doesn't work. It needs to be a constant. Each one of these parts needs to be a constant so that I can change the Vx without changing the Vi, and the truth remains. Does it make sense? Okay, if that is the case, then let us only look at one of those ones over here. If this is the case, let's only look at that. So what we have over here is Vx times g of Vx divided by dg of Vx by dVx is alpha. Okay, if that is the case, then let's separate again variables. And now we are separating in Vx on one side and g's on the other side. Okay, if we do that, then we have on the left hand side Vx, that is the Vx side, and this one here is divided by 1 over, that is dVx, that is this one here. And on the right hand side, we have 1 over g of Vx, and then dg of Vx. And then we still have our alpha over here. And I move the alpha over to the left-hand side. So I have a 1 over alpha here. Okay? Everybody fine with this? Now, if this is the case, I can just integrate it, correct? If I'm integrating it on the left-hand side, this is a constant, so it remains, it's 1 over alpha. The integral of Vx by Vx is 1/2 Vx squared, correct? So there is 1/2, the 2 of the 1/2 is here, and then here Vx squared. And I have an integration constant, of course. So I've got my integration constant plus my integration constant c. And on the right-hand side, I can do that integration as well. The integration of 1 over something is a logarithm of that. So it's a logarithm of g of Vx. And then I would have also an integration constant here on the right-hand side, but I can say my c over here is the combination of those two integration constants. So I don't need to do anything more. Now, if that is the case, we can do a little bit more math here and just say, get out of what we have on the right-hand side, what is really g of Vx. For that, we put the whole thing on the exponential. So if I put it on the whole on the exponential, then I have e of ln of g of Vx, which is just g of Vx. And on this side over here, I have e to the power of 1 over 2 alpha Vx squared plus a constant, correct? I don't like having it written like this. So let's say we write it a little bit different, because if I have e to the power of a plus b, e to the power of a plus b, then that's the same thing as e to the power of a times e to the power of b. So let's first say we have e to the power of c here. So this is e to the power of c, and then times e to the power of 1 over 2 alpha Vx squared. And then I can say e to the power of c, that's maybe just my constant a. I call it a just like I call this one here alpha. We don't know anything about it yet. But e to the power of some constant, which becomes a new constant. E to the power of 1 over 2 alpha Vx squared. Okay, so now I know my distribution function. I know already my shape of the distribution function. I just did some strange math, and it gave me that my distribution function needs to be e to the power of the square of the velocity. Isn't that amazing, right? It already defines the shape. There's still two constants which we don't know, but we actually do know those constants. Let me tell you why. First of all, we know that if we integrate over the whole interval, then we need to get 1 out of it. So we know that the integral from minus infinity to plus infinity over a times e to the power of 1 over 2 alpha Vx squared dVx, that has to be 1. That thing has to be 1. That is a normalization of the distribution function. That's what it says here. The integral over the whole thing needs to be 1, so that the probability is 1 for it being anything. And the second thing, we know one more thing. We also know that that what we did last time, Friday, that it is true. That it is 1/2 and b squared, correct? So we also know that if I'm asking myself, what is the average I'm asking myself, what is the average kinetic energy in the x direction? Then that is, at the same time, 1/2 k Boltzmann times t, because we calculated that on Friday, and it is also the integral of going from minus infinity to plus infinity, now being interested in the kinetic energy, so 1/2 mvx squared times g of vx dvx, because that is how you deal with those distribution functions when you make averages. So I have this equation and I have this equation. I have two equations and I have two unknowns. A, the capital A here, what is my prefactor, and the alpha over here. Two equations, two unknowns. That's nice. I can solve that system. At least maybe the system is solvable. In this case, it turns out the system is solvable. And so you can do the math, but I'm not going to do the math here, and you can find what the values are. And here it's written. So the A is root of the mass over 2 pi kt, if you do that, those integrals. And the alpha is minus m over kt. So the alpha is minus m over kt, so that, actually not, it's 1 over kt over minus m. So that we are getting this one. So if I'm looking at my distribution function for the velocity in x direction, it has the velocity in x direction squared in here. So if I actually integrate over that, I'm back at my arrow functions. I don't need to tell you what arrow functions are. They were in the first homework. That's why they were in the first homework. So all those integrals which we are interested in there, that were arrow functions. The next thing is, if you look at it, what you have over here, the minus sign, and then 1/2 mv squared. That is the kinetic energy in the x direction. And that is divided by, in units of, kt. So the distribution function puts 1/2 mvx squared into units of kt divided by kt. And that is what gives me the probabilities. So let's have a look at how it's shaped. This whole thing is called a normal distribution. Normal because I didn't really need much knowledge about my system in order to find it out. It's the normal thing which comes out of maths. And the guy who figured it out, that is a normal thing, was Mr. Gauss, this Swiss mathematician. And so it's also often called a Gaussian distribution. And it looks like this. Gaussian bell curve, where we have the maximum at 0, and then it's symmetric left and right, has to be. Velocity in x direction and minus x direction need to be the same. And then, depending on what the temperature is, it is really sharp at low temperatures, or it is much wider at higher temperatures. Why at higher temperatures? Because at higher temperatures we have more particles which are faster. But it also means, because the whole thing is normalized to 1, it needs to go down in the middle. It can go above 1 over here, if the interval on the x-axis is short. So that if I integrate over the whole thing, I will still get 1. Okay. Is that making sense? So I have a distribution function now. Now, if I want to know how many particles are in this velocity interval, I just integrate my distribution function over this velocity interval. And now, if I want to know how many particles are in this velocity interval, I also integrate just over this interval. Now, if you have a good calculator, that's what you do. If you have a less good calculator, you need to realize that what you're doing over here is using the error function, and the error function is always integral to 0. So what you really do is you go from 0 to here, and then you minus the 0 to here, because then you get this red shaded kind of area. Depending on how good your calculator is, it can do it for you in fun. But what you have to get familiar with is dealing with the error function in your calculator, and then being able to figure these things out. That is the distribution function for the velocity in x direction. I also would like to tell you what the distribution function for the velocity, for the speed is. What do you think is the distribution function for the speed? Now we know already what the speed is over there. It's still written on the right-hand side. It's still written over there. So it's a positive only value. It is how fast is the particle going, no matter in which direction it happens to go. The distribution function for the speed is typically abbreviated with a capital G. So let's have a look at capital G over here. The distribution function for the speed. Now, that is of course the distribution function of the velocity in x direction times the distribution velocity in y direction times the distribution function for the velocity in z direction. That gives me one point in velocity space. But then I also need to figure out how many equivalent points in velocity space are there where it's going at the same speed, just in a different direction. And that is really the sphere shell in velocity space, which I have. And the sphere shell in velocity space is then, I think, 4 pi v squared, right? V being the speed. That is the radius, 4 pi, the radius squared is the surface area of a sphere shell. If I have small velocity, it's only very few vectors over here, which are there. If I have a long vector, it's a large sphere shell, which I can have there. There are more ways of setting up the larger velocity, the larger speed, and so I have this value in front of me. This looks like a weird mixed function, doesn't it? It has v for speed, and then it has vx, vy, and vz in there. So let's see whether that is actually 4 pi, what that is, v squared, and then g of bx, and g of by, and g of bz, so that is a, whatever my a was, times g of, times e to the power of minus 1 half mvx squared over kt, and then a times e to the power of minus 1 half mvy squared over kt, and then a times e to the power of minus 1 half mvz squared over kt. Now, that is then 4 pi v squared a cubed. Now, if I'm having these ones here, if I'm multiplying e function, I can also just add those ones, correct? So what I'm doing over here, I'm adding these portions in the exponent. And I see they have always the same factor. It's always minus 1 half m over kt. There's the same factor in front of me. So I pull that out. So So I have e to the power of minus 1 half m over kt times vx squared plus vy squared plus vz squared. That, of course, is just the square of the speed. That is 4 pi v squared a cubed e to the power of minus 1 half m over k t times v, the speed squared. And here immediately I have now my distribution function for the speed, which is somewhat similar and somewhat different to the distribution function I had for the velocity next direction. If I plot it out, it looks much different here. If I plot it out, it starts at 0 and goes to infinity. There is no negative speed. And so it is a function which starts at 0 and not a function which starts at minus infinity. And then I have pretty much no probability at 0. There aren't really any particles totally at rest in this room. Some move in x direction, not so much in y. Some move in y direction, not so much in x. That's why I'm getting this kind of distribution. But in total speed, there are practically no particles which have no total speed. And so it starts out at practically 0 over here, and then it has a maximum and goes down again. Okay, so if you do all your math about those a's and so on, you'll get the value. This here is then called a Maxwell distribution, or Maxwell-Boltzmann distribution, and not a Gaussian distribution. So it looks quite different. Okay, at this point, I'd like to talk about the homework and do the rest of this one here the next time. And it seems that in my slide set I'm using the homework. But you actually have the slide set in your homework. Yeah. So let's have a quick look at your homework here. So let's think about the freeway right by campus on a normal day when it's not blocked. Then you have cars moving on that freeway in velocity in x direction, one direction only. Freeway direction is the x direction. Oops. Why am I not projecting? Yes. Then the freeway next to So I ask you to imagine or to measure 125 velocities of cars on that freeway. You're standing next to it, you measure them. Don't just make a random distribution. It's not that some go 15 and others go 75. It's not that wide on that freeway. Get a little bit better estimate on what those velocities are. Put that list of imagined or measured velocities in an Excel file. And then calculate what is the average velocity of those cars, and calculate what is the kinetic energy of each of those cars, assuming a certain mass of these cars of 300 pounds over here. And then make the average of your kinetic energies of those cars. And what you'll find is that the energy corresponding to the average velocity and the average kinetic energy of the cars is not the same value. Wonder about that and tell me about it. All of that in an Excel file. You use an Excel file for that. And using that Excel file for that, it is important that you do it the right way. It is important that when you submit, what's going on? When you are having your Excel file like this, you name your Excel file when you give it with homework 6, because this is homework 6. And then after the homework 6, you have your code names, all 3 code names. And then down here, that is a worksheet what we're looking at. And this worksheet over here, you will name again now homework 6, and it's A, and then your code names over here. Pinky names, whatever your code name is. Or if you have more, and maybe movie and whoever else is there, correct? So we need to have the name both here for the name and there. And here it's 6A, and here it's 6, because now your second homework will be on the second sheet here, and then it will be named homework 6B. And then again the code names. So it will be homework 6B. And then again your code names. Don't forget that, because the TAs will probably move those Excel sheets all into one Excel file. And if they do that, and you don't write it over there, all the information is gone. Now, if you are asked to write some text, then please write that in the cell in your Excel file. That way, it's only one document that the TA sends you. Make your Excel sheets neat, so that the TAs don't have a hard time. The second problem is also assigned. It's a little bit more difficult. It is, imagine an interval. Imagine an interval which has a certain length, and then see how many points are there. So if you have an interval from -5 to +5, like here, then you have whatever many points in that. If this is 0 over here, then a radius of 0 will have 1 point inside, a radius of 1 will have 3 points in it, a radius of 2 will have 5 points in it, a radius of 3 will have 7 points in it, 4 and 5 you can do. That is for 1D. In 2D, you also have an axis like this, and your radius of 0 will have 1 point, your radius of 1 will have 5 points in it, your radius of 2 will have how many points? Make Excel count it for you. And then also do it in 3D and still have Excel counting the points. Make an index, and from the index you derive the points, and then make Excel count it for you. If you have a problem with that, we are there to help tomorrow doing those. Thanks,